section 9.2 is going to take what we did in section 9.1 and extend it one step further. So you notice these title says Multistage Experiments now. So the idea would be that instead of selecting just one card out of the deck, now I'm going to select maybe 2 or 5 or something like that. More than one event is happening one after the other. That's the idea. All right, so to start with, and we could have introduced this, I could have introduced this in the last section, it just wasn't really all that helpful because it wasn't necessary yet. We're going to work with tree diagrams. So just to show you hands real quick, who's seen tree diagrams before? Okay, a few of you have. A tree diagram is actually a way of organizing our information in a visual, it's a visual way of organizing our information. A one-stage experiment has one node, so like one little dot, and then we draw all the outcomes out from that dot as branches of, if you will, a tree. So let me do, let's flip a coin. And if you flip a coin, you have one option of heads and one option of tails. There's only 2 things can happen, right? Now, if I either flip 2 coins or flip a single coin twice, one option is that the first coin, or on the first flip, I get heads or tails. But then after that flip, I have to do it again, or do it with another coin. So I could have gotten a heads and another heads, or the first coin could have been heads and the second coin could have been tails. The first could have been tails with the second heads, or the first could have been tails with the second tails. So you end up with a multi-set of branches when you're doing a multiple step tree diagram. Yeah, multi-stage tree diagram, that's what I wanted. And we can do it for more than 2. Could I flip the coin a 3rd time? Sure. And I would just split each of these at the end into 2s, right? Heads and the tails. And what's more is that we can actually write the probability of each of these things next to them. For instance, and maybe I'm getting to this later, can't remember. Oh, yeah, I am. So let me come back to this picture after I say it on the next slide. All right, there's a multiplication rule for tree diagrams. So for all multi-stage experiments, the probability of an individual outcome along any path of the diagram is the product of all the probabilities. So you have this written on your notes. Let me go back and show you what it means, and then we'll finish the slide. So if I have a coin, we just talked about a coin a minute ago, what's the probability I flip heads? 1/2. And tails? 1/2. So on each stage of my multi-stage diagram, we're going to do the same thing. Heads is 1/2, tails is 1/2. So the second time I flip the coin, I still have a 1/2 chance of heads and a 1/2 chance of tails on each one of these. But you see, what this tree branch right here represents is getting 2 heads. And the way I find the probability of getting 2 heads is I multiply the probabilities along the branch. So 1/2 times 1/2 is, what is it? 1/4. Sorry, I thought I heard 2/4, just checking. Okay, we're not adding, we are going to be multiplying. So we've got 1/2 and 1/2, and that's going to be 1/4, right? So there's a 1/4 chance when I flip a coin that I get, flip one twice, that I get heads twice. So this one would be 1/4. What's the chance that I get a heads and then a tails? It's 1/4, because there's still just 1/2 times 1/2. What's the probability I get a tails and then a head? 1/4. And then get a tails and a tail? 1/4. Now here's the deal. If I were flipping 2 coins and they were indecipherable, so let's say they were both pennies and neither one was shinier than the other, they both look equally as gross or whatever. Okay? Flip the 2 coins, you're not really deciphering what's going on except for what the outcome looks like. Then, while each individual outcome here is equally likely, you are more likely to get 1 head and 1 tail than anything else, right? Because there's 2 ways on this tree diagram for that to have happened. So this first outcome right here was getting a heads followed by a heads. This one was a tails and a heads together, as was the second one. And I realized that the order is reversed, but if the coins were indistinguishable or if it just didn't matter, right? Whoops. Then these right here would be the outcome of getting 1 head and 1 tail. So while each of them are equally likely, individually all by themselves, if you distinguish between the coins, they're not equally likely if you're not distinguishing between the coins. Does everybody see what I'm saying? We're going to encounter this again in a minute, later in the lesson, I believe. So I just want to draw your attention to it here. All right, so note. This is a big note because it doesn't actually explicitly say the directions. I want to see a tree diagram every time you get one of these. Every single time. I'm going to take off if I don't. Okay? So it's not going to say draw a tree diagram, but you're going to do it anyway. So make sure you allow yourself the space to do that if you're skipping around in problems or something like that, which some of you do sometimes. Okay. Independent events are the occurrence where one of the, can't talk. This happens when one event does not actually affect the next event. Okay? So that actually happened on my previous example. First time I flipped the coin has no bearing on what happens the second time I flip the coin. Completely independent events. Okay? But not all events are like that. For instance, if it rained yesterday, that will affect the chances of whether it rains today. Right? I mean, there's a relationship between the weather patterns between days. So just because there's an equally likely chance today and tomorrow doesn't mean that when we combine them, those are independent events. Now, probably your weather pattern today is not directly affecting your weather pattern in August, right? So we might be able to talk about those being potentially independent. But today and tomorrow's weather, they're related in some way, okay? All right, so for any events, it depends. Oh, I don't have this written down. What did I need? 9 to 7. I didn't get this written. Check it out. I think they're less. This is the multiplication one. Check it out. Yeah, it is. All right. So for any independent events, if you want the probability that the events both occur, so like the idea that I get a heads followed by another heads. Oops. So if you want events 1 and event 2 to occur, then this is actually just the probability that event 1 occurred times the probability that event 2 occurred. And as long as the events, are independent, we can multiply the individual events together to find the probability that both happen. That's actually what we did on the tree diagram. We actually multiplied along the branches because in that particular description, we were looking at independent events, right? Flipping this one. All right. This one does not have independent events. But you can still draw a tree diagram, and you can still do the multiplication. But let me show you what happens. All right. An executive committee consists of 10 members, 4 women and 6 men. 3 members are selected at random to attend a meeting in Hawaii. What is the probability that all of them are women? All right, so we're going to select member number 1 for the team to go. And we have 2 options. I mean, I know we have 10 different people, but we have 2 options based on how we are distinguishing between the people. What are the options when I select member number 1? Male or female, right? What is the likelihood that I select a male? 6/10. And I'm just going to leave it. Well, you can either reduce it now or you can. Let me leave it because of what we're going to see happen in a minute. Let's leave it at 6/10. All right, so what's the likelihood that I'm going to select female? 4/10. Okay, so I've got the first person selected. It's like you put them all in a hat and you randomly pulled one out. We had a 4/10 and a 6/10 chance of them being a man or a woman. That's how all we're distinguishing. All right, but we aren't just taking one person in Hawaii. We're taking 3. So I'm going to select a second person. And again, the same options occur. I could either get a male or a female. The difference is this. There are not still 10 names in the hat. How many are there? There are now 9 people's names in the hat. And it matters whether I picked a man the first time or a woman the first time. So I don't have, just like on the last problem, all the same probabilities everywhere with 1/2, right? If I selected a man already, how many men are left in the hat? 5. Out of how many total? 9. 9. Because I already picked one of their names. How many women are still left in the hat? 4. Actually, all 4 of them, if I select a man the first time, out of 9. But it's not going to say 5 ninths and 4 ninths on the next branches. Because the next branches hinged on the fact that I drew a woman's name first. So if a woman's name was drawn first, how many men are still in the hat? 6. How many names are still there? 9. How many women are still in the hat? 3 out of 9. Now I've selected 2 people with this diagram to go on the trip. But how many was I supposed to pick? 3. So I need to do the diagram one more step. Okay, I've got male, female on all of these. All right. So along the first branch here, I have selected 1 male, 2 males. How many males are left in the hat? 4. How many names are left in the hat? 8. Let me change colors so that I'm not writing into things and unreadable. All right. Second branch, however, I selected 1 man, 2 men, and now I'm going to select a woman. How many women are left in the hat? All 4, right? Out of 8. Still 4 women in the hat along that first branch, because no women have yet been selected. All right, next branch, still male and then female. So I've got 1 man, 1 woman. How many men are in the hat? 5. Out of how many people total? 8. In fact, on the last draw, there's always going to be a denominator of 8, right? Because no matter who I picked 2 names out of the 10, there are 8 left. So all my denominators are going to be 8. We really are only counting how many men or women in each case we've got. All right, the second case then, if I've got 8 in the hat, how many of them are women? 3. Right, so each of these branches has to add up to a probability of 1. That's also true. So if I've got 5 here, I've got to have 3 here. Notice in the first branch I had 4 and 8, and I had 4 and 8. Total of 8 people. Okay. All right, let's do the bottom half of our diagram. The bottom half of the diagram, I had 1 female and 1 male. So how many male names are left in the hat? 5 out of 8. So if there are 5 male names out of 8 in the hat, how many female names are there? 3 out of 8. All right. This last piece, I've already selected 2 women to go on the trip. Right? So how many men are still in the hat? 6. The same 6 I started with out of 8. How many women are left in that hat? 2 out of the 8. Now, do you guys remember the problem from last time that some of you kind of looked at and said, wait a minute, and you raised your hand? What was it about?
Socks.
Socks. It was about colors of socks, right? You could do the colors of socks problem in this very same way, except that you had 3 colors of socks, right? There was black, blue, and green, brown, whatever they were. There's 3 colors of socks. So instead of having 2 branches coming off everything, you would have 3 branches coming off everything, because every time you reach into that drawer, as long as the colors are all still there, you have 3 different things you could be pulling out. Okay? Now we're not done with the problem. All we've done so far is draw the diagram.
What grade would you teach this in? I feel like it would be so confusing.
With tree diagrams, it would be upper elementary school.
Yeah.
Yeah, it would be upper elementary school. But tree diagrams are used in elementary school for sure. Yeah. And this is a more complicated example, right? Like you would not start with this example, agreed?
Yes.
No. But the heads and tails example is not too bad.
Yeah, that isn't bad.
Probability in general is being taught in late elementary school, whereas it used to not have been. That is more common. All right. Each of these branches can be multiplied, agreed? Now, you don't have to multiply all your branches, but you could multiply them out if you needed to find any of those particular probabilities, right? What probability are you being asked to find here? The 3 females. So do I need to multiply out 8 probabilities? No, I don't. I only need to multiply out the bottom one, right? I need to multiply out, in fact, let me do it this way. This branch. So I need to multiply 4 over 10 times 3 over 9 times 2 over 8. You can reduce some of that before you multiply if you'd like. In fact, let's do that. How does 4 over 10 reduce? 2 fifths. How does 3/9 reduce? And 2/8, 1/4. All right, and if you want to, right now, you could reduce one more step further. What could you reduce? Somebody said the 2 and the 4 could be reduced here if you want. If you don't reduce them now, you're going to have to reduce them later. So if you reduce them now, you're going to end up with what on the top? 1 and what on the bottom? How many? 30. Yeah. If you didn't reduce it, you would have had 2 over 60, and then you would have had to reduce. Either way, you're going to reduce. So it is not real likely that you're going to take 3 women on the trip, is it? No. If there is a 1 out of 30 chance all 3 people go on a trip are women, and then you were asked, what is the probability there's at least 1 man? What could you do? Yeah, you could do 1 minus 1 over 30, right? All of the other options that are on this diagram have a man in it. Yeah? So, again, one thing you could do is you could just do 1 minus the 1 over 30 and you get 29 over 30. What's another way you could do it? That's going to be much, much harder. You could add up all the other probabilities, couldn't you? So you could find each of these other 7 probabilities and add them up. Not probably your most convenient way of doing it, and yet at some point, somebody's going to try and do something just like that. So try when you're looking at the problems to think, is there an easier way of doing that? Because if you're adding up a whole bunch of probabilities, there probably is an easier way of doing it.
So these get a lot more like harder.
This is one of the more confusing ones you're going to see. You're not going to see much worse
So like
than
I
this.
think this would be so easy just to take the chance. Like not to do the tree.
Yes.
I mean, I know you said to.
Yes.
But
Yeah, so your question of, would you have to do a tree to do this, or is there another kind of way to do it? Yeah, you could do this without a tree. But on some of the problems you're working with, it's going to make it a lot more convenient to do it that way. And the reality is, if you were teaching this, you'd be teaching them to draw the trees. So I want to see trees. Yeah. All right, here's another example. We've got a box that contains 5 slips of paper, numbered 4, 6, 7, 8, or 9. The first player reaches into the box and draws 2 slips of paper and adds them up. If the sum is even, then they win. If the sum is odd, then they lose. Okay, so they've reached into the basket and they've drawn 2 numbers. Now I could draw a tree diagram for this. This would be fine. We're going to actually list it out much like we would draw a tree diagram without the drawing part, which is okay too. So one option is that we could get a 4. Okay. We're drawing them out one at a time, and we're not replacing them. I know you guys saw some of those issues of replacing, or at least you saw that phrase listed at one point or another in your last little assignment. Didn't really affect a lot, but it's going to affect things now. So if I draw a 4 out and I hold on to it, and then I draw another slip out, I can't draw out another 4. Does that make sense? And that's in essence what's going on here. They're reaching in and they're drawing out 2 slips at the same time. So you can't get 2 4s if there's not 2 4s in there. Is that okay? All right. So if I draw a 4, what could I draw after I draw my 4? A 6. Or I could draw a 4 and a 7, or a 4 and a 8, or a 4 and a 9. And that's all the ways that I could draw out a 4. And I'm writing it with addition because eventually the problem talks to me about how I'm going to have to add them together, right? Okay, so we're going to get that. I might not draw out a 4 at all. Agreed? So if I don't draw out any, if I draw out a 4, this is the only options I've got. If I don't draw out a 4, what could I draw? Okay, can I start with 5 next? Or I'm sorry, 6 next? Yeah. Sorry, there isn't a 5 on this one, is there? 6 and 7. Okay, or 6 and 8, or 6 and 9. Okay. Kind of what I'm doing right now is I'm listing out the sample space, right? I'm listing out all the different ways this could happen. I'm not exactly doing it in a tree diagram, but I've got very much the same feel of what's going on. No, because we already did 4 of this. And since you're drawing both out at the same time, that was one way that can happen. Yeah. What else? 7 and 8, or 7 and 9, or 8 and 9. So this is, in essence, if you want to think about it, this is your sample space, right? That's really what we did. But the issue is whether or not we win or lose the game. And the issue about winning or losing had to do with it being with what? What was the condition?
Sun is on.
whether the sum was even or odd. So let's go find all my sums. So 4 plus 6 is 4 plus 7, 4 plus 8, 4 plus 9. Good. 6 plus 7, 6 plus 8, 6 plus 9, 7 plus 8, 7 plus 9, 8 plus 9. Okay, the question is, oh wait, did we get the question? It's on the next slide.
What is the probability?
Yeah, next slide. What is the probability the player wins? So the probability that they win is the probability that it comes out that the sum is even, right? Isn't that what it said?
Yeah.
Okay. All right, so how many even pulls do I have?
4.
4? How many total different options do I have? There are 10 of them. And this reduces to 2/5. Now we're going to change the game. All right, so this is the kind of thing that you see happen at carnivals, right? The issue is that you can't be always losing, or you're not going to lose if you're the person running the carnival booth. Okay? So this game right here makes it less likely that you're going to win than you're going to lose. Agreed? Because you only had 4 out of 10 ways of winning, whereas there were 6 out of 10 ways of losing. But if you change the game slightly, it can change the results drastically. This question says, does the probability change if the two numbers are multiplied as opposed to added? Okay, so we have the same things that we had before as my sample space, except what? They're multiplied. So I have 4 times 6, 4 times 7, and 4 times 8, and 9. Thank you. I have 6, 7, 6, 8, and 6, 9. I have 7, 8, 7, 9, and 8, 9. I can find all of these exactly if you'd like, and you certainly can. But I claim that most of you just know. These are all even. These are all even. And that one's even. Oh, this one too. How do I know those are all even? Yeah. One of the multiples, right? One of the numbers that's being multiplied with is an even number. So I'm going to get an even result. So, does the probability change if the numbers are multiplied? Yes. The probability of getting a product even is actually what? What is it? 9/10. So you can just change the game a little bit. If the person who's running the game doesn't understand what's going on with the numbers, they're just being told these are the rules of the game, they wouldn't realize that they changed it in such a way that really changed the result, right? All right, let's look at another one. This one's got spinners with it. Suppose an experiment consists of spinning spinner X, this is spinner X, and then spinning spinner Y. Find the following. All right, so this is a lot like the question that you asked me at the beginning. I think it was Megan that asked it, maybe it was somebody else. No, maybe it was Charity. That asked about sample space, right? So sample space is simply listing out all the ways that something can happen. So this is my sample space. Sample space is a set of curves and curly braces. What could happen when I spin first spinner X followed by second spinner Y? I could get a 1 and a 1. What else could I get? I could get a 1 and a 2. What else could I get? A 1 and a 3. And there's nothing really special about me writing them sort of as ordered pairs, except that when I did it, you knew exactly what I was talking about, didn't you? So it's just kind of a convenient notation for this particular one to look at. But I didn't roll or spin a number 1 at all. What else could happen? A 2 and a 1? Or a 2 and 3. Do you have a question for me, Emily? Okay. All right, so is this okay so far? There's no probabilities. There are only numbers here in the sense that they were marking sort of locations on the picture. They really even aren't really numbers, right? It's just a list of different options. Now we're going to find some probabilities. So this is the first one, the probability of spinning two even numbers. 1, 6. There's only one of those on there, right? And it's important to realize that at least the way that they're drawn is that this is a 50-50 chance of getting a 1 or a 2, right? And this one over here is a 33% chance, if you will, a 1 out of 3 chance of getting each of them individually. Okay, that's allowing me to make the claim that these are all equally likely to happen. All right, so there's 1 out of 6 ways that you could get an even number. How about getting at least 1, 2? Okay, so what was it before you reduced? There are 4 of those on there, 6 total. So you've got a 2/3 chance of getting at least 1, 2. What about getting, oops, I'm sorry. What about getting exactly 1, 2? 3/6, which is 1/2. Okay? All right. I promise these numbers cannot be right. But when I buy a new shirt for my son, there's a probability of 0.15 that he will stain the first time he wears it. I'm quite certain it's higher than that. If the shirt is stained, there is a probability of 0.2 that I will not be able to adequately eliminate the stain. That means that it still will show. Okay? What is the probability that my son's new shirt will be permanently stained after the first time he wears it? So, I mentioned we're going to draw something on almost all of these, and that thing was what? A tree diagram. And we can do that for a situation question just like this as well. So the first description had to do with what in this problem? Whether he stained it, right? Okay. So this is whether he stains it or he doesn't. Now if he doesn't stain it, then obviously once it goes through the wash and it comes back, it's still not stained. So you're assuming that I don't do something crazy with the wash and like throw a crayon in there or something like that, right? Okay, so the only part of the tree diagram that continues after this is whether or not I was able to eliminate the stain that did happen. So this tree diagram actually looks like this. There is no second branch coming out of the do not stain area. Okay? The assumption being made that when it comes out, it's clean. If it gets stained, what happens? I'll use that. It either comes out or it's permanent, like it stays. Some description of that is fine. Anything you've got there. So, what was the probability it said that the stain comes out? It's actually 0.8 because it actually told you the probability that it's permanently stained is 0.2, right? So there is a 0.2 probability that I will not be able to get it out. So the question that was asked then was, oh, I didn't write this in here. The probability it was stained was 0.15. Not stained was what? 0.85. All right, so let me write this in. The question that was actually asked, though, what is the probability that after he wears it will be permanently stained? So the tree branch that this is talking about is this one, right? So how can I find out the probability that when he wears that shirt the first time it comes out stained? I multiply, right? 0.15 times 0.2, which is 0.03, I think. Is it 0.03? 0.03, isn't it? So a 0.03 probability or a 3% chance, that's what that's saying, that the one he wears it the first time is stained forever. Yes,
why wouldn't it just be 0.2?
Because some of those shirts that came out clean because they weren't stained to begin with. So imagine that I had 100 shirts that I bought for my son, which would be a little over the top.
Just a little bit.
A little bit. Well, 85 of them, when he wears them, don't get stained at all. So they come out of the wash, they're clean. 15 of them go through the wash stained. Because he wore them, they were stained. Of those 15, I have an 80-20 chance of actually removing that stain when I wash it. So what ends up happening is that there are 3, it says 3 down here, 3 of them out of that 100 are permanently stained after he wears them the first time. Make sense?
I'm just confused. Never mind, I think I confused myself. We'll figure it out.
Okay.
Yeah.
Let me know if it still sticks when you can't figure it out later. All right. Joe says that if a family has 2 children, then the only possibilities are 2 boys, 2 girls, or 1 of each. Because there are only 3 possibilities. The probability of having 2 boys is 1/3. Is Joe correct? Explain. I already see Kayla shaking her head. So the answer is no, he's not correct. Why not?
Well, like it was all like 1/4 down the line, but you can have a boy then a girl or a girl.
Okay, so one thing I could do is I could draw the tree diagram. I can also explain it the way you're using your language to do so. It says no because you could have what?
A boy first.
A boy and then a girl, or a girl and a boy,
Boy first.
2 boys, or 2 girls. Those are the 4 different arrangements that you could have if you had 2 children, right? So the probability of having 2 boys is actually what? There's actually a 1/4 probability of having 2 boys. Make sense? Okay. All right. Has anybody ever heard of Huntington's disease? Kayla, have you heard about it from me?
No, I'm sure.
There's a couple of different dramas that have used it recently. Private Practice was one of them. Another one that I saw it in was House. What have you seen it used in?
They also had it on a show called Snap. It's for real.
It's for what?
It's for real. Like
Oh, like the real example.
yeah,
Real life.
a mother like killed her 2 sons because she said they were separated.
There was a thing on Oprah that was very similar to that too. Probably what this was based on. It was actually a mother with 2 daughters on Oprah. But Huntington's disease, who's actually heard of it, like to the extent that not just on a crime show, like does anybody know what it is? You know such a
Well, because I think her too.
Okay. Huntington's disease is somewhat akin to Parkinson's disease. Okay, so Parkinson's disease is like affects your central nervous system, starts shutting down certain operations your body can't control anymore. And it does it by overproducing a certain chemical in your body, and it's related to your DNA. So you either have it or you don't. It's not something you develop over time. It gets worse over time, but you either have it or you don't. Much like when you were born, you either had 2 X chromosomes or an X and a Y. Okay, the have it or don't kind of thing. Huntington's runs in my family. My grandmother had Huntington's disease. And the way that it works is this. When you have Huntington's disease, when you have children, they each have a 50-50 shot of getting it. A lot like when you have children, you have a 50-50 shot of having a boy or a girl. Right? So aside from genetic mutation, if your parent doesn't have it, your parents don't have it, then you can't have it either. Okay? My grandmother had Huntington's disease, and we found out in 2001 apparently that my father has it as well. And at this point, my father has it pretty drastically. It's very obvious. My son asks questions every now and then. He'll ask questions about Opa is what we call my dad. He'll ask questions about why Opa walks around like this. He's stupid over. He'll ask questions about why Opa right now carries Kleenexes with him everywhere. And he has real difficulty trying to control his saliva. That's his deal. My grandmother had a really difficult time. And my dad does too with his walk. And so he looks like he's walking like this. Kind of. It's very unsteady gait. There's a lot of other symptoms of Huntington's as well. One of the things I specifically remember from my grandmother with Huntington's was that I remember going to like a Golden Corral, or imagine like Cherry Berry or something like that, where you control the lever of the ice cream. Okay, and the time that it would take for her brain to tell her hand to stop the ice cream, she'd have ice cream everywhere. Okay, it slows down your central nervous system. In 2001, my parents decided that they were going to tell everybody what Grandma had. And by the way, your father has it too, which means you all have a good shot of having it. My brother, my sister, and I. So what we're going to do on this problem is we're going to do exactly what I did in my head that night. We're going to do with tree diagrams. But what did in my head, what went on in my head that night when my parents decided to tell us this. Okay? So I am the oldest. So this one is me. Okay? So this node, if you will, is me. And there's two possibilities. Okay? Again, it's not one of those things that you either have or it's one of those things whether you either have it or you don't. So one possibility is that I have HD, Huntington's disease. The other possibility is that I don't. And each of those probabilities, given that my father has the disease, is what? 56, so it's 1/2. Or you could use decimals if you want to do 0.5. We'll do 0.5 just for fun, because I've done fractions on all the others. All right, so that was me. I was born, I either have it or I don't. This is an independent event, right? It has no bearing over the next child. So after I was born, I have a sister. So this is my sister's chances. My sister also has two options, right? She either has it or she doesn't. And the likelihood of each one of those branches is 1/2. I have a second sibling, a brother. My little brother, who is like 6 inches taller than me. So you have brothers like that. Not so little anymore, it confuses my children. How is your little brother being 6 foot tall? Well, my little brother is born, and he has the same situation that I and my sister each individually had. He either has it or he doesn't. And each one of those branches have a 0.5 on them, or 1/2. Now, we could multiply these branches together, and we're going to need to in a little bit anyway. And these are actually really easy to multiply because they're all the same, right? So what happens if I multiply any one of these branches together? What happens? It does get smaller. What number do I get? 0.125, that's right, Haley. So each of these are a 0.125 probability. And it'll help us to have them for the next slide. So let me write them in. Problem A is what I did in my head the night when my parents told us this. I sat there. We were living in Kansas at the time, and we were visiting for Thanksgiving. Ray came to tell somebody on Thanksgiving. By the way, everybody has a debilitating disease. So we sat there. We were at my parents' house, and my husband and I talked about it. And this is exactly what I did. I said to myself, "What is the probability that at least one of us three has it?" Myself, my sister, and my brother. Now, there's two different ways to do that problem. Somebody tell me one of them. What could I do to figure out what is the probability that at least one of us has the disease? Okay, so Kayla's all interested in doing this the easy way. So what do you want to do, Kayla?
Find out the probability of none of y'all.
And then what would you do? Right? These got to subtract it from 1. So there's only one way that all of us come out of this thing and are okay. It's the very bottom, right? One of those tree branches. What was the probability of that one tree branch? 0.125. What's 1 minus 0.125? 0.875 is an 87.5% chance that one of the three of us has Huntington's disease. And that's really scary. Because I know what Huntington's disease has done to my family. And it is really scary. The only reason my parents decided to tell us about it at all was because using in vitro fertilization, you can actually not have a child with Huntington's disease if you choose to use it in that way. So what they do is they harvest a certain number of embryos and create them, right? And then what they would do with in vitro is they would implant them back into the mother's womb. Everybody kind of know what this is? Well, if you let the embryos grow to 8 cells, is what it takes. When you test those embryos, you can see whether the embryo, the child, has Huntington's. And if your interest is in not having a child with Huntington's, you discard the ones that have Huntington's and only implant the ones that do. This is why my parents decided to tell us, was because there was this possibility. This is new research. My husband and I said, we're not going to do that. And we made the decision that if we had it, if I had Huntington's, we were not having children. And it was not a popular decision. My family was very unhappy with that idea. Very unhappy with that idea. So in 2003, I decided to get tested. We moved back to Oklahoma at that point. We were living in Norman. And we started the process in August. It's a lengthy blood work process. It is just a blood work process. They took like 4 vials of blood or whatnot. They spin it and they count. They're counting. They're looking at your DNA, right? So they're not like looking for antibodies of something or something like that. They're actually looking at the triplet repeat counts of the A's and T's and G's, and I don't remember what the other letter is, on your DNA. I'm not a science person. Some of you guys probably know a lot more about science than I do. Those are counting, and everybody has a certain gene, and you can count it on anybody's, but you have no desire or reason to do so unless you're in my situation, potentially. So I went, and I got tested, and I do not have Huntington's disease. So remember, again, you either have it or you don't, so it's not something I'll develop later. But I do not have Huntington's disease. Because I do not have Huntington's disease is the reason I have my daughter. We would not have had my daughter. Isn't that a scary thought? And that's the reason that it was not a popular decision when we made the decision to be tested and to have that sort of that line of thinking with my parents, because they said, well, if we made that decision that we weren't going to have kids, then we wouldn't have had my brother, my sister, and I. And my husband and I said, okay, but that's looking backwards. You can't do this process looking backwards. The only thing we have to go on is moving forwards, what we're going to do. But I will tell you, because of Huntington's disease affecting my family, and my husband and I, for 2 years, did you see that, right? It was 2 years between the time my parents told us and the time that we decided we're going to go get tested. During that 2 years, we said, okay, but not having kids is not an option. We're going to have children. We just decided that if we didn't decide to have children biologically, we would adopt. And God made it very clear to us during that 2 year time span that regardless of what happened with that test, we were supposed to adopt. The reason I have my son is also because of Huntington's. It's because we had to actually make those decisions and think about what's the other option? What else are we going to do? What? And we said, you know what? This isn't God's plan B for us. This is part of his plan for us. So because of Huntington's, I have my son. Now, the reality is, I still have a brother and sister, and neither one of them have been tested for Huntington's. My sister has 3 children. My brother has 2 children currently, which means that I still have a brother and a sister and 5 nieces and nephews that are at risk for Huntington's. We're going to do the process again, but we're going to do the process for just my brother and my sister, because the reality is, this is where we are. We're down here, because I don't have it. But my brother and my sister still have the possibility that they do. So if we take this tree diagram and we only do the bottom 2 branches, we have it or we don't, just like before. And all of these individual branches, you know what they are. What are they? They're all 0.2 or 0.5, yeah. We'll get to the 2.5 in a minute. So each of the branches, and when I multiply them, somebody already said it, they're not 0.125 now. They're just 0.25 this time. So in spite of the fact that I don't have it, what's the probability that one of my siblings still does? Yes, it is. It's 1 minus the same branch at the bottom that we used before, except that it only has the 0.25 on there, or 0.5 on there twice. I'm terrified. So there is still a 0.75 probability, or 75% chance that one of my siblings, at least one of my siblings, has the disease. I'll tell you that I've gone to a conference, a Huntington's conference. The number of people affected by this is relatively small, but I've gone to a conference about Huntington's before. And there was a family that we met there that they had, it was like 12 or 13 grandchildren. And they had made the decisions along the way that they were testing. I mean, each of the children made a decision to get themselves tested. And all of them had it. All of them had it. Now, the likelihood that all of us has it is just as likely as the likelihood that none of us does. So that's the reality of the math. I mean, the numbers still work out the same way. But that's pretty scary. So the Oprah episode that my mother-in-law saw, and it's similar to what Kayla was talking about, is that there was a woman who nursed her mother through the end stages of Huntington's disease and had herself tested. And the reality is that once you're tested, you either have it or you don't. But the reason that we made the decision prior to having children, and the reason that my sister won't make the decision right now, at least in part, is because she can't have any of her children tested. You could test when they're still in the womb. So you could test with the intent to abort if they had it. I don't really think that's a good plan. You could do that, that's a possibility. But once the child's born, you can't do that any longer. My sister has 3 children, my brother has 2. If they ever, either one, found out that they have Huntington's, they have to wait until each of their children are 18, and their child who is 18 now gets to make that same decision that I have to make of whether or not to be tested. So, just a little bit of my history today.